Okay, let's see some questions that involve halogenoalkanes from past exam papers. Let's begin with this one. Halogenoalkanes react with a number of different reagents in nucleophilic substitution reactions. A sample of potassium cyanide, so potassium cyanide, dissolved in ethanol, is added to a sample of 1-bromobutane, here its formula, and heated under reflux. A nucleophilic substitution reaction occurs and compound A is formed out of this nucleophilic substitution reaction. Name compound A. Well, obviously the bromine, the bromide ion, bromine from this compound has been replaced with a cyanide ion. So, I mean, let us write this one in the initial, the 1-bromobutane molecule. How would it be? Bromobutane, butane, 4 carbons, 1, 2, 3, 4 carbons, and bromine there at the end. All the others will be hydrogens. Okay, so this would be the molecule. After the substitution, this bromine atom will be replaced with this part here, this ion, the cyanide ion. So what would be the result? Would be again these 4 carbons, 1, 2, 3, 4, with the hydrogens, but instead of bromine now we'll have this cyanide ion. So we have an extra carbon now here. We have 3 and plus 2, 5 carbons. So this has become now a pentane, but with a proper suffix there. So this would be called pentane nitrile, because this is the nitrile ion. So the name of this compound is pentane nitrile. So this is the name of compound A. So whenever we have this type of reaction, the substitution reaction with a cyanide ion, we see that the carbon chain increases by 1 carbon. Yeah, so be careful, this is now pentane, not butane anymore. All right. Now, the next question says, what is meant by the term nucleophile? Well, nucleophile, here is an example. What determines a nucleophile is it has a lone pair of electrons, we can say. So one acceptable answer would be that it has a lone pair of electrons. Or we can say this is an electron donor, electron pair donor. The pair is important. Electron pair donor. So electron pair donor. And of course we can see that it attracts and is attracted to positive centers. Okay, so that is enough. Now what is meant by nucleophile? Something that has a lone pair of electrons. Now, identify the nucleophile in this reaction. Well, here it's our nucleophile. We can write it. The cyanide ion, in other words. The cyanide ion, in our case, is the nucleophile. Okay. Explain why this reaction is described as a substitution reaction. Well, obviously because we had the bromine. The bromine atom was substituted. The bromine atom was substituted or replaced by the nitrile. Bromine atom replaced or substituted by the nitrile. All right, and the next question, which is the last one on this page. Okay, what does it say now? State the reagent or reagents and conditions needed for our compound, which was 1-bromobutane. Let's write it up there, 1-bromobutane. So state the reagent or reagents and conditions needed for 1-bromobutane to react to form this compound here, which is an amine, as we can see. What is this? Butylamine. Because we have 3 + 1 carbons here, so it's from butane. So the name of this thing is butylamine. Okay, so state the reagents, etc., and conditions needed for 1-bromobutane to react to form butylamine. And remember, this the reagents must be. We need to have ammonia here. We need to have ammonia. Let's write it in words: ammonia. Ammonia, but this ammonia must be dissolved in ethanol. Okay, dissolved in ethanol, because if it's not dissolved in ethanol, it will not be a substitution reaction. So we need ammonia. The reagent is ammonia dissolved in ethanol, and the conditions must be. We need to heat under pressure, or in a sealed container. Heat under pressure. So we need to know these conditions, and these conditions actually where in your book in page 220, where it says substitution with ammonia in ethanol. You see, if a halogenoalkane is heated with an excess of ammonia dissolved in ethanol under pressure, an amine is formed. So it's the first thing that they are talking about when we have substitution with ammonia, about the conditions. And they always ask about the conditions. So you need to remember this, to know by heart these conditions that are involved in the substitution reactions and in any other reactions. Okay. So here is the end of the first page from this exam paper, and then it continues with a little, again with halogenoalkanes, but in a different setup. Now we have tertiary halogenoalkanes involved in this question. Now let us see here. Equal amounts of 3 different halogenoalkanes are added to 3 separate test tubes. An equal amount of aqueous silver nitrate and ethanol is added to each test tube. So silver nitrate and ethanol, you see dissolved in ethanol, is added to each test tube. The time taken for a precipitate to form is recorded for each halogenoalkane. So here are 3 halogenoalkanes, and you can see the one is with chlorine, the other with bromine, and the other one involves iodine. And the time taken for the precipitate to form in seconds is given here in this column, and we see the top one, the top halogenoalkane, takes 460 seconds to form some precipitate. And compare this with the bottom one, which takes only 40 seconds. Obviously, this precipitate forms a lot faster in only 40 seconds in comparison to the top one. Okay. Now, describe and explain the trend in reactivity of the different halogenoalkanes shown in this experiment. Okay. So if we look at this in this column, obviously the time for the precipitate to form gives us quite an important information here. The top one takes a very long time to form, 460 seconds. Then the next one takes 190 seconds, and the last one takes only 40 seconds, appears very fast. So we see that as we go down the column, we see that an increase in reactivity. The reactivity increases, therefore the precipitate forms faster here. So we can say here we see an increase in reactivity. describe and explain. So what does it mean now? Or if it's easier for the precipitate to form as we go down the column, which is down the group 7 elements, isn't it? What does it mean? It means that the bond between carbon and the halogen, here we have carbon and chlorine, carbon and bromine, carbon and iodine. The bond between carbon and the whatever halogen is connected to the carbon is easier to break, obviously. So in other words, the strength of this bond decreases as we go down the column. So as we go down the column, we can say that there is a decrease in the strength, in bond strength, which means it's easier to break it, strength. It's easier to break the bond. That is why it's easier to react as we go down that is why the reactivity increases as we go down the column. Okay, so what can we say? We see an increase in reactivity down the column, down this the group 7 elements. So the increase in reactivity. We try to explain now why. What do we see that explain the trend? We see that the trend that there is an increase in reactivity as we go from chlorine to bromine and then to iodine. And why? Because the bond between the carbon and the halogen becomes weaker. Or we can say we see because there is a decrease in the bond strength because of this bond exhibits because of a decrease in bond strength. It doesn't make sense that because the bond of this decreases, we can say in strength to make some intelligible sentence here. Because the bond between carbon and the halogen decreases in strength. So it is easier, and it's easier to replace the halogen, So this gives an explanation of this trend that we see in the table. So the increase in reactivity from chlorine to iodine, this is the trend, and this can be explained because of the decrease in bond strength between the carbon and the halogen, which means it makes it easier to replace the halogen, to break this bond and replace the halogen, okay, and the precipitate to form. All right, now the next question says, all 3 halogenoalkanes tend to react via this mechanism, the Sn1 mechanism, okay? Explain why this mechanism is favored. Now, this is a very important question, and we're going to see it very often when we look about the mechanisms of in the halogenoalkanes. And we need to distinguish between tertiary and primary halogenoalkanes because this S1 mechanism only applies to tertiary halogenoalkanes. And here, all these halogenoalkanes that they're giving us here are tertiary. Let us see tertiary. Why are they tertiary? Say, for example, this top one. We see that this carbon that is connected to the chlorine is also connected to another 3 alkyl groups. And can you see that? For example, if this is this carbon here, which is connected to the chlorine, the other 3 bonds of this carbon actually connected to three other carbons, three other alkyls. In this case, we have the methyl connected to this carbon. So we can see that this carbon here is a tertiary carbon. Okay, so this is a tertiary halogenoalkane, and the same applies for the other two. So now, because this is a tertiary halogenoalkane, the mechanism by which the substitution, nucleophilic substitution takes place is this special mechanism, which is called Sn1 mechanism. Okay, they do not ask us to draw here this mechanism, but maybe we should actually. What would this mechanism be all about? It happens in two steps, this mechanism. Need some space. Say that we have this halogenoalkane. Usually bromine is the most common alkane that we use in substitution reactions. Let's use the the 2-bromopropane. So these are the alkyls up there to show that this is a tertiary halogenoalkane. What happens in this case of this mechanism is that, be careful now, that this carbon, this part of the molecule and the bromine, it's actually a dipole because the bromine is more electronegative. So this is this part has a negative partial charge. The rest of this carbon has a partial positive charge, represented with a delta symbols. And what happens now is that this first step, in this first step, the pair of electrons moves to the bromine, which has this negative partial charge. This first step happens very slowly, and what remains now is that a carbocation. Carbocation remains behind with these three. Let's call them R so that it's easier to write them. These three alkyl groups, and what remains here is a carbocation, and of course we have the bromine that separates. So this is the first step of the mechanism, which happens very slowly. Okay, just the slow step, but very fast now because of this carbocation. If we have in our solution now, actually let me remove that because it's in the way. Let's put it somewhere else. We can have say a hydroxide ion from the solution. What happens now? This will be attracted to the carbocation. That is a very fast step now. It happens very fast, and the result will be, say, the formation of an alcohol. Obviously, since this will be attached to the carbocation, and of course we must not forget this bromine ion that we're left with. Okay, so this mechanism, which is represented by this kind of representation, happens in two steps. The first step, which is the slow step, this is the first step, the slow step, where results in the formation of this carbocation, and then the hydroxide ion is attracted to this carbocation and forms an alcohol. And this is the second step that happens very fast. This is the fast step. This is the first slow step. Now, the important thing is this formation of this carbocation as an intermediate product in this mechanism, this carbocation, which does not happen in the other mechanism, which is called Sn2, which applies to primary halogenoalkanes. This mechanism happens to tertiary halogenoalkanes, like the ones that we have here. So, okay, so this is the mechanism. Now, it's nice to have it in front of us, especially this carbocation, when we need to answer this question. Explain why the S1 mechanism is favored here. And the reason why this mechanism is favored with this intermediate step that has the carbocation is because this carbocation is quite stable in comparison to whatever, to a carbocation that would be formed for a primary halogenoalkane, in which case this carbon would be a primary carbocation rather than the tertiary carbocation that forms here. And the reason, we had said it before, if I remember well, when we were talking about carbocations, formation of carbocations, a tertiary carbocation is more stable than a secondary carbocation, and a secondary carbocation is more stable than the primary carbocation. Here we have the tertiary type, which is the most stable from all of them. And why is it stable? Because this carbon is attached to three other carbons, three other alkyl groups actually. And the alkyl groups, and we need to say that, tend to kind of release electrons or push their electrons towards the carbon, and which means it's kind of, they induce a positive charge on the carbon. Or we can say that because of this release of electrons, or the pushing of electrons towards this carbon, this carbocation carbon, they tend to attract this positive charge on the carbon, and equally. So the charge of the carbon, of the carbocation, is what is the word? Shared more evenly between those three alkyl groups. So the charge is not like concentrated in one place only, but it's shared more equally. The charge distribution, in other words, is more even around the three alkyl groups, and that makes this carbocation quite stable. And so now in our answer here, explain why this mechanism is favored. First of all, it is favored because these the tertiary halogenoalkanes, which means we have the formation of a tertiary carbocation. So they are tertiary. We have to say that, it's very important, tertiary halogenoalkanes. So they are tertiary halogenoalkanes, which means there is a tertiary carbocation formed as an intermediary state. Tertiary carbocation forms. We have the formation of a tertiary carbocation, which is stable, stable. We have to say about the carbocation, about the tertiary, about the stability of this carbocation. We have to say all that. And why is it more stable? Now we have to give a short explanation of why this carbocation is more stable, because due to the free electron releasing, let's say, methyl groups, or alkyl groups. In this case, we have methyl groups, or, which have a positive inductive effect. So positive inductive effect on the carbocation, and that is why it is more stable. So something like that, okay. So it's important to know the difference between how the tertiary halogenoalkanes behave and how the primary halogenoalkanes behave. The primary would not undergo this mechanism, they would undergo this mechanism. This is for the primary, which it's not our case in this example. We have tertiary halogenoalkanes. Then the next one, identify a halogenoalkane which tends to react with an aqueous solution of silver nitrate and ethanol via this Sn2 mechanism. So they want us to give an example of another halogenoalkane that will undergo this mechanism. And as we said, this mechanism is the one undergone by a primary halogenoalkane. So what could be any example that has a primary halogenoalkane, like for example, there is one, what would it be, where the halogen, in this case the bromine, would be connected to the last carbon at the end, in other words, not in between. That would be a primary halogenoalkane. What is this? One with 3 carbons, one bromopropane. That would be one bromopropane. Propane. That would be an example of a halogenoalkane, which is a primary one, and this will undergo this type of substitution reaction. Okay. So there we are. And now we can stop. We can continue. Next week, it's nice to, I want us to do one more example with halogenoalkanes. Yeah, next week. And then we can continue with alcohols and so on. Okay.